I think you can check YouTube now.
Okay, sir. Now it is streaming. Yeah.
Yeah. Yes, sir, it is working. So now we are starting now. Okay, sir. Thank you.
Okay. Good afternoon, everyone. Today we have the seventh lecture in the weekly online lecture series on radar meteorology, jointly organized by South Asian Meteorological Association and Cochin University of Science and Technology. Today we have our speaker, Dr. Devendra Pradhan, sir. And before starting the presentation, I welcome Dr. Swagata Baira for the welcome address.
Thank you, Dr. PPC caller. So, very good afternoon from Indian Standard Time, which that I have added this Indian Standard Time, learned from Ovila sir. Ladies and gentlemen, I am Sagato Para, and it's my great honor to host this prestigious lecture series. I would like to extend my heartfelt thanks to our partners and the organizing committee for their unwavering support and dedication. We are privileged to have with us today some of the most respected figures in meteorology. We are excited to have Dr. Devendra Pradhan sir, who will share insights on the topic analysis of archived sequences of different thunderstorm, hailstorm, and their analysis based on DWR images and different wavelength radars, concept of DB, DBZ, DBM, DBW. Additionally, we have sessions covering few eminent scientists before. These lectures are designed to foster collaboration and innovative thinking, providing you with practical tools and knowledge to apply in our work. I encourage each of you participate actively, share your ideas and network with fellow professionals. Your contributions are invaluable. Together, through collaboration and knowledge exchange, we can make significant strides in advancing meteorological science and addressing the pressing issues our region faces. I am confident that this lecture series will be a catalyst for innovative solutions and lasting partnerships. Let us embark on this journey of discovery and progress together. With all the best wishes, I welcome all the guests, participants, and organizer ACARR CUSAT to the South Asian Meteorological Association lecture series. Thank you. Thank you, Dr. Srikala.
Thank you, sir. Now, I welcome AVM retired Professor Ajit Tyagi, sir, for the presidential address.
Yeah, good afternoon. I'm audible and visible?
Yes, sir, you are audible and visible.
Thank you so much, and sorry for some glitch in my enabling me to connect to you, and thank you for providing the panelist link. Swagata has covered the importance of this training, and of course we are lucky to have Dr. Pradhan to deliver a series of lectures. First, he started the program series with the first two lectures, and today he is again going to cover very important aspect of the radar observing system with respect to the thunderstorms. Because for nowcasting and short-range forecasting, this is the most powerful tool, and also when it is embedded with the bigger systems also, the radar is able to bring out the salient features of thunderstorm, heavy rainfall. So that is a very, very powerful tool. Aviation and other early warnings of associated with thunderstorm, the radar provides. And nowadays, that data is also being assimilated in the NWP models for short-range forecasting. So in all, this radar, apart from most of us see just the visible part of it. visual appearances of thunderstorm, but a lot of important information is in various parameters which Dr. Pradhan will be covering. It provides insight about the structure and the associated weather of the thunderstorms from the radar information. So once again, thank you, Dr. Pradhan, to share your vast experience and first-hand knowledge of monitoring thunderstorms from radar scopes. And also, I'm sure in continuation of these lectures, all participants are getting benefited, and this lecture will provide a very important application for both for research and also for operational application. So once again, thanks to the organizers and the ACARR is doing a wonderful job, and we are getting good response from the participants. So make full use of it and ask all doubts which you have within the question answer sessions, and even after that, Dr. Pradhan is always available. Thank you. Have a great time.
Thank you, sir. Now I invite Dr. Devendra Pradhan, sir, for the lecture.
Thank you, ma'am. Thank you, President Sama, Dr. Ajit Tyagi, sir, and other panelists who are joining this training session. At the outset of my lecture, at the beginning, I would like to say that what the apprehension with the people and the students is that the radar is a very difficult subject and it's not able to be understood properly. But on the contrary, I would like to say it is one of the simplest tools for monitoring live, like such as satellite. Only thing that you have understanding should be clear. And for that reason, my today's lecture is prepared in such a way that every beginner who does not know much about the radar, etc., can understand. And since the from the IMD site and from the other places, the images are available in the live mode. So you can see yourself that whether there is a system over your station, wherever you are there, in which direction it is going to move, whether there will be heavy rain, moderate rain, less rain, or whatever is there. So I'm trying to make these things slightly simpler in such a way that everybody should be able to understand. But before that, whenever we are talking about this rainfall and reflectivity value, the first thing is that 30 dBz, 40 dBz, 50 dBz. What's the meaning of this dBz? What's basically dB? What is dBz? And what other things are there? So in the beginning of my presentation, I would like to explain these things here. And later on, I'll give you some exercise to convert this dBm value into the power and dBz into the rainfall. Suppose I say the reflectivity shown is 45 dBz. Nobody can say that how much rainfall is there. If I convert it to the rainfall rate, we can understand, okay, this 45 dBz is equivalent to so much of the rainfall rate. So we are expecting, say, moderate kind of the rain. Or if it is 55 dBz, it is an intense rain. If it is 65 dBz, there is a chance of the cloud burst. So these things we should understand well, and we should see the things accordingly, that how we have to prepare the things. So let's start with the presentation. I'm sharing my screen now. Are you able to see?
Yes, sir.
Yes, sir. Yes, sir.
So I'm coming to the slide mode.
YouTube now.
So, okay, let's start. I'll welcome all your doubts at the last of the lecture now. So let's start that what we are going to discuss today. Concept of dB, dBm, dBw, dBz, classification of thunderstorms, analysis of the archived sequence of thunderstorms, hailstorms, their analysis. So this is my
lecture series on
today's topic. So you might have heard the word decibel. The intensity of the sound is 50 decibel, 60 decibel, 70 decibel.
Sir, one more.
I welcome
I
Dr. Swagata.
think your YouTube is running.
A welcome address.
I think your YouTube. Thank you, Dr. PPC caller. So, very good afternoon from Indian Standard Time.
Whose YouTube is
Did this Indian Standard Time? Someone's you learned from Ovila sir.
Yeah, I think yours, sir.
Is this okay?
Yeah, yes.
Should I continue now?
Yes, sir. Yes.
Yes, sir, you can
Okay.
continue.
So you might have heard every time that the sound intensity strength is 50 dB, 60 dB. And recently in the World Cup series, you might have seen that in some cases when this India won the series, yeah, that is a World Cup here. That time the loud intensity has gone to 115 dB and sometimes 120 dB. So what is the meaning of the decibel now? First, I'm going to explain. Basically, it is a unit of the power. When in general we use the unit watt, but when it is compared with some reference power, then we call it as the power in the decibel here. So decibel is basically a logarithmic expression comparing the reference and the output or whatever is the sound intensity or strength we are getting now. So it is defined as power in dB decibel is equal to 10 times log to the base 10 P out upon P in. The meaning of the P input is some reference. So reference may be some 0 dB or 2 dBs or 5 dB or some power reference is there, but where we are calculating about the power output. So if power output is equal to twice of the PIN, then you can see here P output upon P input, it will be 2. So power in dB is equal to 10 log to the base 2. Its value is 3.03. That can be taken as approximately 3 dB. It means when the power is doubled, that time it is as good as 3 dB increase in the strength. Therefore, 3 dB power is equivalent to twice the reference power. Similarly, when P out, power output is equal to 10 times power input, then decibel power will be 10. Please remember, I hope everyone knows about the logarithmic scale. Logarithmic scale is a linear scale, whereas other scales may not be linear. For example, if you write A is equal to X into Y multiplied by Y. So if you take the log A is equal to log X plus log Y. It means it becomes a linear scale. So in that case, when the power gets 10 times multiplied by 10, so equivalent increase is 10 dB. So we say the 10 dB power is equivalent to 10 times the reference power. It means when we are multiplying the power in terms of dB, we have to increase, that is adding or subtracting when there is a multiplication or division. So this is the basic introduction of the decibel, that it is a logarithmic expression 10 log to the base 10 P out divided by P in. It is in general. Now, when we take some reference power, for example, our reference power is 1 milliwatt. It means reference power or input power is 1 milliwatt. So when our reference is fixed as 1 milliwatt and we are comparing the output with reference to the reference, power that is 1 milliwatt, then we say, okay, we will call it as dBm. So dB small m, it means the decibel power in terms of 1 milliwatt reference. So reference is fixed. I take another example. If you want to measure the height of the roof of our room, we say, what is the height of the room? Suppose somebody says it is 12 feet, 11 feet. But the question is, what is the reference? Whether the reference is ground, floor, or the reference is the height measured from the table, or the reference is somewhere else. So the height of the roof of the room will change and it will depend upon the reference. If the reference is floor of the room, we will say 11 feet. If there is a 3 feet height, table is there, and if you are measuring the height with reference to the table, then we'll say it is 8 feet and so on. So reference is a very important term that is to be kept fixed, and hence when we say dBm, it is the unit of power, and when the reference is 1 milliwatt. So power in dBm is equal to 10 log to the base 10 output power with reference to 1 milliwatt. Input power is a fixed reference. It means when output power is 1 milliwatt, input power is reference power is 1 milliwatt, it will be cancelled out and we will be getting power in dBm is 0 because log 1 is 0. It means when we say 0 dBm, it is equal to 1 milliwatt power. When we say 3 dBm, it is equivalent to 2 milliwatt because increment by 3 dB is equivalent to multiplication by 2. In increment, when it is from 3 to 6, the multiplication is from 2 to 4, that is twice. So when it is coming to be 10 dBm, we find that 10 dBm is equivalent to 10 milliwatt, that is 10 to the power 1 milliwatt. When we say it is 20 dBm, there is an increment in the power by 10 dBm. I am repeating, there is an increment by 10 dBm, the power gets multiplied, it is 100 milliwatt. When the 30 dBm is equivalent to 100 milliwatt, that is 10 to the power 3 milliwatt, but 10 to the power 3 milliwatt is nothing but 1 watt. It means 30 dBm when we say it is 1 watt. Now we are increasing it. 40 dBm on the power side multiplied by 10, 10 watt. 50 dBm again multiplied by 10, 100 watt, that is 10 to the power 2. When it is 60 dBm, the equivalent power is 1000 watts, that is 10 to the power 3 watt or 1 kilowatt. I hope you could understand well. When we are having 0 dBm, 1 milliwatt, 10 dBm, 10 milliwatt, when it is 60 dBm, 1 kilowatt. Now we have multiplied the power and incremented in dBm. Let's go in the opposite direction. Now we are dividing the power. 0 dBm is 1 milliwatt. If we divide by 2, so it is half milliwatt. So in place of the increment, we will have the decrement here, subtraction by 3. So it is minus 3 dBm, half milliwatt, minus 6 dBm, quarter milliwatt, minus 9 dBm, 1 upon 8 milliwatt, minus 10 dBm is 1 upon 10 milliwatt, is 10 to the power minus 1 milliwatt. And please remember, now we want to have one-to-one matching our identity between the left-hand side and our right-hand side. See here, minus 10 dBm, 10 to the power minus 1 milliwatt. So minus 20 dBm, 10 to the power minus 2 milliwatt, minus 100 dBm, 10 to the power minus 10 milliwatt. So this is basically the analysis of dB, then reference power 1 dBm, and now we have come to the dBm on the plus side, dBm is on the minus side. So you should understand the power 1 milliwatt is 0 dBm. When we are incrementing it, power is multiplied by 2. Incrementing by 10, power is multiplied by 10. On the other side, when we are reducing the power, dividing it by 2, by 4, by 8, accordingly, this table gives the idea that how the dBm is understood by milliwatt power. So now we need not to get confused. What is the meaning of dBm? dBm is the unit of power when the reference power is 1 milliwatt. Small m is 1 milliwatt. Now, when we talk about this dBW is slightly bigger. Now, as you have already seen, if it is m, reference power is 1 milliwatt. So if it is dBW, means reference power is 1 watt. When reference power is 1 watt, the power is expressed in dBW. It means power in dBz is equal to 10 log to the base 10 P out when the reference power is 1 watt. It means power in dBW is 0 if output power is 1 watt. Clearly means 0 dBW is 1 watt. Increasing it, I'm sorry, it is not 3 dBm, it should be 3 dBW. By mistake, I have written this dBm, but it should be So what I do now, okay, let's understand now from here itself. It is not 3 dBm, it is 3 dBW 2 watts, 6 dBW 4 watts, 9 dBW 8 watts, and so on. So you can correct in your notes if you are making it. It is in the case of the watts, it is dBW. I'll correct my presentation slightly later. So this is an introduction of dB, dBm, and dBW. Now, this is a very common term, radar reflectivity factor, and we denote it by Z. Now, what is radar reflectivity? By the name itself, we can understand from the radar, when echoes are received after the transmission of the electromagnetic waves from the hydrometeors. Hydrometeors are what? Water drops, snow, ice, graupel, hails. These all are called hydrometeors because they contain water in the basic form. So radar reflectivity factor, it means that factor which is coming after the reflection or the scattering from the hydrometer received by the radar is called radar reflectivity factor. In the common terminology, we say, what is the reflectivity or what is the radar reflectivity? Our intention is to know about the Z, but remember, Z is not only the reflectivity. Scientifically, we say radar reflectivity factor represented by Z depends upon the sixth power of the drop diameter in the sample volume. So formula for radar reflectivity factor is Z is equal to summation di to the power 6. And what is the meaning of this summation? That you can understand well, that we are, just a moment please. So di means we are summing up the drop diameter for the all drops inside the sample volume, and to the power 6 means we are taking the sixth power. That is, there may be some small drop, there may be some bigger drops. So reflectivity is the sixth power of the drop diameter. It's a very significant quantity. It means if you are having 1,000 smaller drops and one big drop or 10 big drops, in that case, the contribution to the Z will be more from the bigger drops rather than the smaller, so many smaller drops. And then you can calculate very well because it is going to be power 6. And now this explanation was required because whenever there is a high value of the reflectivity dBz value, then it will be an intense rainfall, heavy rainfall. Why? Because the high reflectivity means there are the bigger drops. When the bigger drops are there, when they are coming as a downpour here, it will create a torrential rain or the heavy rain. And sometimes when the reflectivity value, Z value is very large, 64, 65 dBz, in that case, it might contribute to the cloudburst. So what is cloudburst? That we will discuss later on. But this was very important, that Z is equal to summation di to the power 6 per unit volume. The unit of Z is, to be noted, millimeter to the power 6 per meter cube. Now, our cloud is containing smaller drops, millions and billions of the smaller drops of the different diameters, 0.1 millimeter, 0.2 millimeter, 1 millimeter, 0.5 millimeter. It means there are the millions of the billions of the drops are there of the different sizes, smaller and the bigger. So if you are having the spectrum or the contribution of all Z, it will not be a linear scale. It will be some exponential because it is going to be power 6. And then there will be a huge amount of the data will be there. It will not be linear. So it is thought that if you take the logarithmic of Z, logarithmic scale of the Z, if you take the log Z, then instead of going to the exponential curve here, this will become a linear scale. And therefore, we are expressing it in terms of the dB scale, and we call it as dBz, which I am coming to the next slide. So I'm repeating again. radar reflectivity factor is Z, which is directly proportional to the summation means contribution of so many drops, sixth power of the drop diameter, and unit is millimeter to the power 6 per meter cube. So the question is millimeter to the power 6 because drop diameter is measured in millimeters, and per meter cube because the sample volume is in terms of meter cube. So for the sample volume, we cannot take the millimeter. We can take the meter as a standard one. So to be noted, the unit of Z is millimeter to the power 6 per meter cube. Now I'm coming to the concept of DBZ, which is very, very important because throughout the world, wherever there is a radar, there is always a reflectivity. Whatever is there, it is expressed in terms of DBZ or DBZ. Sometimes DBZ, DBZ, depending upon the pronunciation term used from different one country to the another country. So what is the concept of DBZ? The standard unit of radar reflectivity factor Z is DBZ. Z we understood, di to the power 6 summation, and it is the logarithmic expression of the Z given by dBz is equal to 10 log to the base 10 Z divided by the reference. Reference is what? 1. So 1 is the reference. So dBz once again is a decibel value of the Z is equal to 10 log to the base 10 Z with reference to 1 millimeter to the power 6 meter cube. And this dBz should be understood very nicely that what is the meaning of dBz. Because nowhere in any of the countries with any standard radar, nobody is using Z or Z. They all use only the dBz. Now, dBz, as I stated in the beginning here, that a layman cannot understand the meaning of 30 dBz, 20 dBz, 40 dBz, 60 dBz. But a radar person should know what is the meaning of 23 dBz, 30 dBz, 35 dBz, and so on, so on, so on. Larger the value of the dBz, the greater will be the potential of the rain or the thunderstorm. So we should well understand here that what's the meaning of dBz. Now I am coming that this dBz value can be transformed from reflectivity into the rainfall rate, and there is an empirical formula to convert Z into the rainfall rate. Is Z is equal to A into R to the power small b. Z is equal to capital A R to the power small b, where A and B are empirical constants, and as per the Marshall and Palmer suggestions, A is taken as 200 and B is equal to 1.6. So if we put A is equal to 200 and B is 1.6, this relation Z is equal to 200 R to the power 1.6 is known as Marshall-Palmer relation, because they have given the values A is 200 and B is equal to 1.6. Now the question is, why do we accept this formula? As per the practical experience and the research, it was found that this formula A is equal to 200 and B is equal to 1.6 suits to different kinds of the rains very well, because the values of A and B change from place to place, season to season, rainfall to rainfall, country to country, and in the same country, at the two different places, the values of A and B will be entirely different. So this was the one of the biggest problems in converting the Z into the R with the single polarization, because I am talking of the single polarization radar. Whereas in the dual polarization, this problem has been overcome now by going to the different parameters which are obtained from the dual pole radars. So dual pole radar will be taught by some of our friends here, those who are expert in this radar meteorology, and then they will discuss that in the dual polarization radar, this ZR relation is slightly significant, but may not be required very well, because from other parameters only you can find out what is the intensity of rain. So ZR relation is basically translating Z into the rainfall rate. But remember, we don't have to use it directly because we have to take the log. And dvz, for dvz, the formula is z is equal to AR to the power B. First, we will take the log. Log z is equal to log A plus B log R. Then we will multiply it by 10. 10 log z is equal to 10 log A plus B times 10B times log R. So this 10 log z is known as dBz. And then we can convert the value from the z to the r by taking anti-log and other things. So that discussion we can have later on. But some of our participants, they want to, they are raising their hands because they want to know something about doubts. But as I requested, we will have the doubts class after the lecture is over now, because I'm going to show few things which are very important to you. So this was one of the important things that I have discussed here. I'm proceeding further. Now, before proceeding here for the understanding of the thunderstorm, I just ask you, do you think that all the thunderstorms, whatever be the thunderstorm or the hailstorm is there, do they move with the same velocity? This is a very important question, and its answer is equally important. My question is, do all thunderstorms move with the same velocity? Whatever thunderstorm we see by the radar, do they move with the same velocity? Answer is no. Why? Because the thunderstorms are having, the clouds are having different structures. Some are smaller clouds, vertical development or the height of the cloud is less. Some are very tall. In some cases, the precipitation is more. Some cases, precipitation is less. Where potential energy is more, potential energy is less. So if anybody is asking to a radar person whether all thunderstorms move with the same speed, you say no, because the thunderstorms have their own structure. And from my experience, because I did my PhD in a thunderstorm, and then I analyzed more than 500 thunderstorms in the different categories. So this is my research or my opinion, which I'm presenting to you now, that there is a classification of the thunderstorms based on two things. One, on the basis of the structure, and another on the basis of intensity and the precipitation. So now we are going to see the very important thing, classification of thunderstorms as seen by Doppler weather radar. So remember, in general, if you have no radar or you have no knowledge of the different kinds of thunderstorm, you can see, okay, this thunderstorm is there. We are finding it after say 3-4 hours, it will come to us. But no. Not all thunderstorms are having the life of 3 hours, 4 hours. No. The life may be 30 minutes, the life may be 35 minutes, the life may be 1.5 hours, the life may be 3 hours, depending on the structure of the cloud and the thunderstorm. So what's important, if there is a cloud here about 150 kilometers away, which is seen by the radar, and if I say it will come, no, this is wrong. Because I have to see its structure, its movement speed, at what speed it is coming, whether it is coming in my direction, continuously it is coming as per the wind speed or not. So wind speed, wind direction is very important. The potential or the energy inside the thunderstorm is very important. The structure is important. So I made this classification of thunderstorms as seen by Doppler. Structure wise, we have divided into the 4 parts. One, single cell thunderstorm, multiple cell thunderstorm, one is squall line system, or a supercell thunderstorm, basically in the 4 categories. So now let's see what is the definition of single cell storms. I am defining it because this is not a standard definition as per the meteorology. As per my experience, I'm just putting it. Maybe some deviations can be there with the different authors. A single cloud development which moves independently without merging with any other cloud. Single cloud development moves independently without merging with any other cloud is termed as a single cell storm. Now, this is the identification. Next, such storms normally occur in environments where the winds are relatively light and vertical wind shear is equally small. So these two things will support the single cell storm here. So this is the environmental conditions that in under what conditions the single cell storm will be formed. Now third question, how long it will last? The life of such storms is usually 60 minutes to the 90 minutes from the development stage to the dissipation stage. It means in 1 hour or 1.5 hours, it will grow, develop, mature, and it will dissipate just in 1.5 hours. That's all at the most. But the last statement of my presentation is very important. Such thunderstorms move with average speed of 40 to 45 kilometers per hour. Please remember, the potential is not much, but they move with the speed of 40 to 45 kilometers per hour, and the overall duration is around 1 to 1.5 hours. So my question is, if radar is looking for some storm which is around 150 kilometers, a single cell storm, only one single cell thunderstorm is there, it is not merging with the others, will it travel 150 kilometers? Your answer will be no. The reason is it will just dissipate within grow, develop, grow, and it will dissipate within 1.5 hours, and it is 150 kilometers away. Since it is moving only 40-45 kilometers, it will travel only 60-70 kilometers, and it will die out, it will dissipate. So a forecaster cannot say by looking only the cloud that it will come unless he has the knowledge that at what speed it is coming here. And radar is getting observations every 5 minutes or every 10 minutes. So we can see the sequence that how the system is coming in a particular direction. But if the knowledge is there for the single cell thunderstorm, that can be understood well. If it is 150 kilometer, a single cell, the vertical extent is not much. No, it is not going to come at your place. It will dissipate in between. This is one example. You can see here that this is a single cell which is having some intensified precipitation here, and the vertical development can be seen on the top side where the scale is divided into the 4 parts: 4.5 kilometers height, 9 kilometers, 13.5 kilometers, and 18 kilometers. So at the center, this red color which is showing you the intensity in terms of the DBZ, it is quite intense, but it is a single cell thunderstorm here. So even if it is moving in some place, now it is at the border of India and Bangladesh. So it is going from India towards Bangladesh. But I don't expect that it will move more than 50-60 kilometers. So we can have its prediction that a single cell thunderstorm can move only 50-60 kilometers at the most, not beyond it, unless it is merging with the others. So if it is moving independently as a single cell, within 50-60 kilometers, it will dissipate. Now, what is multi-cell storms? These storm systems consist of a series of evolving cells which typically form on or near the periphery, storm periphery at 10 to 15 minutes interval. It means one cell, another cell, the third cell, and then they are joining with each other. When they join with each other, their energies, the potential energy that you know very well, is joined together, and in that case, it becomes a multiple cell instead of a single cell. Each cell eventually becomes the dominant cell of the storm complex because there are one, second, the third. So then every cell becomes the dominant cell. This dominates from one side, another is dominating from other side, and building to higher levels and approaches in the finally merges with the main complex, and then it will form a single system. So this will become a stronger system when the 2-3 cells are joining together, then merging, and then they are forming a multiple cell storm here. Now the life of such storms when it is having a bigger complex here, usually 2 to 3 hours, means when one cell will emerge, another will emerge, then they will combine, then they will grow, and then they will dissipate. This may be 2 to 3 hours, maybe 2.5 hours or like that. Another thing is there, such thunderstorms also move with the average speed of 40 to 45 kilometers per hour. But sometimes I observe that the speed can be 50 to 55 kilometers per hour because a multiple cell thunderstorm has got a lot of strength, lot of potential, lot of energy. So that will move faster. And in that case, lot of turbulent activities will be there in the environment. So the speed can be for 50 kilometers per hour on an average, but usually we keep slightly. And when then we're looking for every observation, because radar is giving new observation at every 10 minutes interval. So we can see the previous one and the next one in the 10 minutes. So how much distance is traveled in the 10 minutes multiplied by the 10, 6 times. So it will become the speed in 1 hour. This is a simple multiple cell thunderstorm. And if you see here, by zooming it, we can see that there are some three thunderstorms are there here. Smaller thunderstorms are there, which are coming now. And you can see that independently, these are the 3 cells which can be seen here. So this is a maxed image. And then this maxed image gives you the idea that in the range of around 250 kilometers, this is a multiple cell thunderstorm, which is having a sufficiently large potential. And this is then observation from Kolkata radar. Now, another thing which is very important, I should say, squall line, a terminology which is used for the chain of thunderstorms which are joined together, not 1, 2, 3, 4. This might contain 5, 6, 7, 8, 10 number of thunderstorms which are making a chain or a line. And not necessarily only the line. This can be in the form of a curve. It is maybe concave shape or maybe a convex shape, whatever is there. We can find out that this kind of the system is known as squall line, because squall is the term when the gusty winds are there and they are going for more than 40 knots, then we call it as a squall, wind squall. So these squall lines are basically the thunderstorms which are joined together and its length is more than 60 kilometers. This is the basic definition of a squall line, a chain of thunderstorms joined together whose length is more than 60 kilometers and width to length ratio is 1:10. Structure is sometimes linear, but most of the time it is a bow echo. Bow echo means maybe convex from one side and concave from the other side. When the strong winds are there, it is making it more concave on the other side. So these are called bow echoes in the form of the bow. More the convex is the structure, more intensity is the system is. The life of such storms is usually 3 to 6 hours. From development to 3 to 6 hours. Please remember, it can be 3 hours, 4 hours, 5 hours, and maybe more than that. I'll request all participants to please keep your questions reserved for me, which I'll discuss later on. And such thunderstorms move with the average speed of around maybe sometimes 70 kilometers per hour, 80 kilometers per hour, sometimes 100 kilometers per hour. So, and when they're moving with this speed, it means the wind which is associated with the thunderstorm is equally strong, 80 kilometers per hour, 90 kilometers per hour. It means this is one of the deadliest structure of the thunderstorm, and that can create a big problem, specifically with the, I should say, the aviation is most affected by this squall line. And whenever there is any squall line occurrence is there or the severe thunderstorm activity is there, then it is having a lot of turbulences when the plane is going up, and when it is passing through a thunderstorm, then there will be turbulences. It is going up, it is going down. And recently in the news, I have newspaper, I have read that in so many countries there was a turbulence, and because of that, the one aircraft, it came around 60, 70, around 100 feet, suddenly it came down. So the passengers, their head got struck with the this thing here, all the shelves, etc., which were there. So this is very dangerous kind of the system. So when the radar is there on the front screen of the aircraft, they should be able to know they should not enter that region which is having a big squall line or the big system is there. So sometimes if they can see, they can just avoid it, but sometimes it is very, very dangerous, especially this kind of this squall line. So this is, and this I show you. Now another thing, height of the associated clouds may be of the order of 16 to 18 kilometers. When we see from the naked eye, we cannot find the extent, vertical extent, and sometimes the radar is termed as the electronic eye of the forecaster. Because in the normal eye, we cannot see, we can say there is a gray cloud which is very tall, but very tall does not have any quantification. Quantification means we should be able to know that it is 10 kilometer, 12 kilometer, 16 kilometer. So I found that under my studies, that sometimes the height of the cloud has gone to 16, 18 kilometer, and sometimes the cloud top reaches to around 20 kilometers, crossing troposphere and going to the stratosphere. Strong downdrafts of the order of 100 to 100 kmph may be originated by such small line. What is downdraft? From the base of the cloud, then they are going striking with the ground, and then they are coming up. So when they are striking the ground and coming in upwards in the form of J, English alphabet J. So they go like this and they come back. So when they are going down, aircraft is feeling a pressure from the top, and when they are coming up, aircraft is getting a pressure from the bottom. And in that case, when there is a landing or there is a takeoff of the aircraft, this kind of the downdraft, sometimes we call it as a microburst. These microbursts are very, very dangerous, especially with the landing or the taking off of the aircraft. So a radar meteorologist should issue the warning whenever there is a squall line. They should say, under this situation, no aircraft should be allowed to land or should be allowed to take off. And I'm going to show this, the longest I have ever seen in my life is this squall line, which you can see here. This was the max image, max in dBz. You can see the strength of the precipitation everywhere, red color, deep red color, not less than 50 to 53 dBz. And the length of the squall line is more than 300 kilometers. This was the day, 31st May 2014, over Kolkata. In the morning hours, this is 3 GMT UTC. It means as per Indian Standard Time, it was around 8:30 in the morning. And that day, or in the morning, 8:30, there was a complete darkness over the Kolkata city. Airport was completely dark. There was a heavy downpour, and almost 10 flights were delayed, and around 15-20 flights were diverted, because already from the Indian Met Department from Kolkata, the warning was issued that we are expecting a large squall line, large thunderstorm. So from around 7:30, 8 o'clock till 9 o'clock, there should not be any takeoff or the landing of the aircraft here. So this is basically the squall line. And this thing I confess here that I have never seen such a big squall line bigger than this. But there is one more kind of the thunderstorm that is called supercell thunderstorm. Supercell storms are larger, intense, and persistent. Normally produce more severe weather than other type of the thunderstorms. So what is a supercell thunderstorm? Let us understand its structure. A highly organized internal circulation that reaches near steady state enables the supercell to propagate it continuously. It is basically a single cell which is very intense, only one cell, but it is very intense and very large in size. Usually associated with hailstorms and tornadoes, and it has been observed that whenever there is a supercell thunderstorm, it will be associated with some tornadoes. 1 or 2 tornadoes are always there, and some hailstorms will also be there. The life of such storms is usually 6 to 8 hours from development to dissipation, and sometimes more. Such thunderstorms move with average speed of 70 to 80 kilometers per hour. So these things are there that we can understand that what are the different kinds of the thunderstorms. And here you can see one sequence I have made here, observed on 12th March 2003. And then you can see that this over Bankura, BNK, and that is in the eastern part of the India. And you can see here, this is when I'm zooming it, you can see here that how big is the system here, and its height is equally good, very large. It's around 13-14 kilometers. And how the system moves, let's see now. So this is one picture one. Now this was the image which was observed on 8:48 UTC. Another one you can see, the third one, because it is moving towards east. Fourth one slightly dissipated. But if you see carefully that from the behind there is one more thunderstorm which coming here, and that will give it the energy to the forward one. But one thing which is very typically seen here in this, that there is a animal-like kind of the structure inside it. You can see here, because there will be some kind of the high intensity core, and whenever there is a high intensity core and which is having a different kind of the reflectivity, it is making this kind of the structure. I hope everyone is able to see now that this system is very intense, and it has generated 2 tornadoes that day. The system is moving further, now further intensifying and going towards Bangladesh here, crossing the India-Bangladesh border, and it is gone. And that day it has traveled more than 6 to 7 hours. You can see here, it has gone deep inside the Bangladesh. So this was the supercell thunderstorm. Then I have taken its cross sections, and I found that its core was very typical, and we could see the images like some animal or something is sitting, something like kangaroo is sitting in this lower one, which is shown here. So a typical shape is there with the supercell thunderstorm, which I have put in one of my papers here on the supercell thunderstorms in Kolkata and neighborhood. And when we have taken its vertical cross section, this is the vertical cross section. There also you can see here that inside core is very, very intense. It is more than 60 dB, 64 dB that day. But its structure is, as and when we are going outside the core of the system, then the intensity in terms of dBz decreases. So this was a classification based on the structure. Now another classification based on radar reflectivity factor and vertical extent. And we can define severe thunderstorm, moderate thunderstorm, weak thunderstorm, and very weak thunderstorm, 4 categories. What is a severe thunderstorm? Now it is, as I said, it is my study and my definition. So thunderstorm in which the height of 50 dBz reflectivity is more than 16 kilometers has been considered a severe thunderstorm. It means up to 16 kilometers, the reflectivity is maintained till 50 dBz. We call it a severe thunderstorm. Usually multiple cell thunderstorm generate severe thunderstorm. However, the possibility of single cell thunderstorm to become severe may not be ruled out. It has been observed from the rainfall data that such thunderstorms provide heavy rainfall at the rate of 30 millimeters per hour. So you can see here, severe thunderstorm can generate a severe heavy rainfall at the rate of around, it is not in general, but sometimes we can find this. So this is one of the examples on 5th May 2005, and you can see here up to 16 kilometers, the reflectivity is sufficiently high, around 50-55 dBz up to the level of 60 kilometers. 16 kilometers, so this is one of the cases of a severe thunderstorm. Similarly, we can categorize into the moderate thunderstorms when the height of 50 dBz lies within 12 kilometers and 16 kilometers. We call it as a moderate thunderstorm, and it can give the rainfall of the order of 5 to 30 millimeters per hour. Weak thunderstorm, accordingly, we can downgrade it, and very weak thunderstorm. Now I am coming to the part where I am going to show you something, the contribution of Doppler radar towards the 2 cyclones. One was Phylline, which was near super cyclone, 6 to 12th October 2013, and exactly on the same dates, 6 to 12th October 2014, there was another cyclone Hudhud. So I have compared these two images here. To the left, satellite image is there, where you can see a small hole is there, which is nothing but the eye, which is looking very small, but the structure of the cyclone can be seen. And identically at the same time, the Doppler radar image is there, where we can see the eye of the storm very nicely. What we can see here, the core region where there is no wind or the no cloud. So this is basically the satellite image and the Doppler radar image of this almost same time, 12th October 2003, just when it was close to the landfall. This was Hudhud cyclone, and again I have compared these two, where you can see the resolution of the radar is quite high, and we can see so many things with the spiral bands and others with respect to the clouds and the cyclone. Now see here, this is an animation of the satellite image of the cyclone Phylline. This animation gives a beautiful idea that how clearly the eye of the cyclone is seen here. Please remember, when the clear eye is there, it means that it is a very strong system. It is a perfect, almost circular, and this was the case of Phylline cyclone when the category had gone to almost super cyclone. Wind speed was 200 kilometers per hour in the near the eye of the cyclone. And these are the Doppler images. So once again, you can see here to the right, the table is there, and on the table, color table, you can see from the blue towards the red when we are going. 20 means less, 60 means very high, and the system is moving like this. So system is moving towards the coast here. So what's important here? Please see. This eye of the cyclone is the area or the region in which the wind speed is greatly reduced. But when the front part is entering in the coast, then the speed of the wind gradually decreases, and the people are having the apprehension that the system is gone now, and usually they come out when there is a lull period, that is for some time there is no, I should say, no wind in that region. But in the rear part, when the rear part is coming inside, almost the same intensity of the winds is there, and there we can say that it is this time when the rear part is coming here, again the strong winds are blowing, and it can create a big problem, because that time equal intensity winds are there. So radar is giving an information that how the front part is going, how the rear part is going in the coast, and when the cyclone is crossing the coast. Similarly, we are coming to the squall line formation on 31st May 2014, which I have already shown, but let's see it. Satellite pictures were collected from 30th May 2014 till 31st May, and you can see here that one western disturbance has created a severe thunderstorm, and it is moving continuously from the northwest, from the northwest, and it is coming to the east, coming towards the Kolkata, and you can see the intensity of the cloud is very large. It means it was a very strong system that day, which is coming from, once again, you can see it's coming from the northwest and going toward, now it is at the central of India, you can see. Yeah, now it is coming towards. Once again, another loop is there. So this is the case of the 30th May. But since our radar range is only 400 kilometers, so we could not see it earlier. But we are able to see on 31st May, And this is basically the radar observation on 31st May 2014. 0014 means early morning around 5:44 Indian Standard Time, and radar is showing a very strong line which was already there in the north of northwest of the radar. Radar is located at the center here at Kolkata KOL, and then it is showing the squall line here. Now, if we see it, continuous observations show that it is in the form of the bow icon, and it is coming from the northwest toward the southeast. But from the west, if you see very carefully, the small cloud is seen here, which is coming from the behind. And basically, which is coming from the northwest here, exactly northwest, where the PRL and DNB is written here. You can see this squall line is coming from the behind, and it is the same one which is coming from the northwest in the form of a squall line. And now, so what's happening here? These two squall lines are there. So as long as these two are separated here, their intensity is slightly less. But when they combine together, which you can see in the next few images here. So when our forecasters are looking for these two squall lines, immediately the warning is issued that this system is coming, almost coming towards the airport here. And since it is now 250 kilometers away, you can see here, there are 5 circles, 1, 2, 3, 4, 5, each are 50 kilometers. So it is 250 kilometers. And since the squall line is there, its speed of movement may be taken as 70 kilometers per hour or 80 kilometers per hour. So it is expected in the next 3 hours, 3.5 hours. So the system is moving now. You can see here, suppose this is the stage when it is around 250 kilometers. The time is 0034. To be noted, on the top of this image, 0034. And now it is traveling 250 kilometers when it is coming to the Kolkata. This is the time when it has come over Kolkata, traveled around 240 kilometers. The time is 3:04, so not even 3 hours. In less than 3 hours, it has come to the traveled around 240, 250 kilometers. So on an average, its speed is around 80 to 90 kmph. And that day, there was a complete dark over the Kolkata airport. The strong winds were prevailing there of the order of 75 to 80 kilometers per hour. As I already said, 10 flights were delayed and 20 flights were diverted from there because no flight was allowed to land or to take off here. This is the velocity image which you can see here. Few images I am showing you just for information that how the cyclone is looking like, because cyclone lecture is already there over by Dr. Reddy, and some of the events are there. So now I am coming to the one more, that is a thunderstorm event on 26 January 2007. This is a very interesting event that as you might be aware that India is celebrating its Republic Day on 26 January every year. And there is a big celebration and so many foreign dignitaries are invited as the guest here. Prime Minister, Honorable Prime Minister is there, and very, very big senior officers are there, politicians and the ministers, etc. And large number of the people are going to witness this Republic Day parade on this thing at New Delhi. So there is always a question here that will there be any rainfall or any chance of any thunderstorm on that day? So this is analyzed here for 26 January 2017. I'll explain it once again. Let me come back. So before going to the discussion here, let's see that there is one product which is known as VVP2. Okay, so what I do, I have one more presentation which I'll show you, because that presentation is very important, especially with respect to the So I'm showing another presentation. Dr. Swagata, please confirm whether you are looking for this new presentation or not.
Actually, today when I would like to follow Dr. Srikala ma'am.
Okay.
Yeah, we can see, sir, new presentation we can.
This another one, Doppler weather radar. Okay.
Yeah. So
Right.
how long it will take approximately?
Another 10 minutes.
Yeah, sure. Just proceed, sir. Yeah.
Because what I wanted to show here is this one. One very important thing I want to show here. This is the PPI image.
Yeah.
But my more focus will be there on my next slides, where I am going to show about this one product. This is the velocity image, where we can see the eye, and this was explained by Dr. Reddy. Now, this particular image is known as VVP, volume velocity processing. And what is this basically? Okay. This particular image is VVP to volume velocity processing, and you can see the height or the vertical profile of the wind velocity, which is going from almost ground around 300 meters and going up to 7 to 8 kilometers here. And we can see here that where the lines are there, these are known as wind bobs, and it shows that how the system is, what is the speed of the winds at the different levels. So the direction is from south towards the north, and the wind speed can be seen here. So this is basically the wind bobs in the VVP2. And now these are the maxed images of the hailstorm with warning. Whenever there is a hailstorm expectations, there is a setting here. The reflectivity should be somewhere around 50 dBz. Lower height is 2.8 kilometers. Upper height is around 4 kilometers. Because between these two, the freezing level on 7th February was around 3 kilometers. So these two settings are done by the user before going for the observation of a hailstorm. So these are the signatures which you can see on the left-hand side, that these echoes, which are slightly longer, elongated in the form of some elongated echoes. These are the, you can see once again that when you are in this lengthwise echoes, not the circular or some scattered, but these are the lengthwise. These are the signatures of the hailstorm. And now the hailstorm is moving toward the Delhi airport here. And that day, on 7th of the February 2019, there was a hailstorm. And on the bottom, if you see here, it is written here, the protected area at around 10-15 hours, hail warning at 10 at Delhi in the nearby Delhi. So these are the signatures of the hailstorm. So when you are looking for the signatures in the radar, say around when it is 100 kilometers away, so radar meteorologists can easily understand that we are expecting something here. And once again, when it is approaching the airport, which is shown at the center here, so this is coming to the center here, and then again it is going. So that day, for around 2 hours, the intermittent hailstorm was there. So this I wanted to show for hailstorm. But once again, I come back to the previous one where I was showing you. This one. So I was talking about this Republic Day parade here, and then there is always a challenge, and especially to the meteorological department, whether there will be some chance of the rain or not. So this was a big challenge for us when I'm talking of the 2017 when I was working in the department. So there was a question here from the PM office whether there will be rain on 26th of January or not. This was a big question, and since it was related with the our Republic Day parade of our country. So it was a very prestigious event, and we were equally responsible to exactly say that whether there will be rain or not, but we should be focused on this uh, uh, place where the parade was taking place. So this is once again this VVP2, and this wind speed you can see around 20 knots, but the direction was south to north. It means if there is any development in the southern direction, the winds will take it in the northerly direction, and therefore the system will move in the northern direction. You can see that the winds are are very strong now. This is 26 January 2017 in the morning hours, because overnight from the radar is working 24 hours and 24/7 all the days. So from on 26 January in the morning, that is 122, that's around 6:30 in the morning, 6:30, 7 o'clock. So we found that there are some clouds in the north part. This is an image from C-band radar. C-band radar is located in at Delhi and Jaipur, two places in India, and few more are coming up. So we found that some uh, clouds are there on the north of the center of the Delhi, but some clouds are there in the lower part, it's the south of Delhi. So when the upper in the upper part, when the clouds are there, we need not to worry because they will be going in the upward direction. But those are in the downward side, the southern part, they might affect the event. So we were looking on this thing because the wind direction was south to north, but we were sure that there will not be much of the rain. Let's see now how the system was moving. At the center where you can see one aircraft image is there. This is the IGI airport. But just at the center here, just at the middle, center of the screen, you can see the radar was there. And we were all looking from the radar angle that it's going. The system is coming from the south. It's moving as we expected. The system will move in the northerly direction. The system is moving up. You can see here the clouds have not come at the center. They are going slightly in the around say 30 kilometers, 40 kilometers away from the center part where the parade was taking place. And this was the time when the clouds were coming close to this. Time is 4:22. So department has issued the warning of the thunder shower. Thunder may not be there very large, but shower was there, and it was expected somewhere around 10 o'clock. So as per our expectation, the radar was working, and we found around 10 o'clock, there was the rain over the place where the parade was taking place, but the parade was at the verge of completion here. So not much of the effect was there on that event, and event went very successfully. So with these words, I stop here with my presentation. So
so now there will be a question answer. Dr. Madam, you are mute.
Thank you, sir. Thank you, Devendra Pradhan, sir, for your wonderful talk. Now we can have one photo session. So I request all of you to switch on the camera. So Devendra Pradhan, sir, can
yes.
you switch off the presentation?
Yeah, sure. Okay.
Rohini, you don't have light.
Thank you, sir. It's fine.
Okay, thank you.
Now we can have a question answer session. It will be moderated by Dr. Rohini L. Bawal, SP, Pune University.
Thank you, Dr. Shikara. So, sir, this was a very nice presentation. I will start with the first question. Are there any precursors of a squall line?
Please repeat it.
Are there any precursors of a squall line?
Yes.
So
Squall line is not formed instantaneously that it is completed now. But at some distance, some thunderstorms are there, few kilometers away, another thunderstorm. So if in the vicinity, 4, 5, 6 thunderstorms are there, and if they are moving in the almost in the same direction, we can say after some time they may be combined together and it may come in the form of a squall line. So these are the precursors when not only this, from the synoptic observations also we can find out, because that day there will be some temperature will be high, humidity will be large, and in that area some moisture incursion will be there. Some thunderstorm formation, 4, 5, 6 cells will be there in the nearby area. So these are the precursors that it might be converted in the squall line in the next half an hour to 45 minutes.
Sir, continuation of that question. Is there any similar signature of bow echo in a satellite imagery, even on a CTBT kind of image?
Yes, you can find out these echoes, but as I said, when you are looking from the geostationary satellite, which is 36,000 kilometers away, the signatures may not be very clear, but from the polar orbiting satellites, which are at a lower altitude, there you can get something here. But as we are looking from the ground, say the distance is around 200 to 250 kilometers, and resolution of the radar is very good, say around 25 meters to 50 meters, maybe 75 meters, depends upon the type of the radar. So signatures are better seen in the radar as compared to the satellite, but possibilities are there.
Another question. From the radar perspective, what are the reasons for bending the echo in a squall line?
The bending of the echoes, it may not be straight, but it can become a concave shape like this, because there is a pressure difference on the two sides of this line. When the pressure from this side, where the system is coming here, the wind is putting a pressure over that, and on the other side, when the pressure is less, the squall line is converted into the form of the bow echo here. So synoptically, the situation is seen here, but from the radar point of view, if we see, it is not always straight line, or not always this thing here. Initially, it is in the squall line, a straight line, and then sometimes it takes curvature. So because of the curvature, it becomes, and sometimes it becomes S-shaped also. I have seen in some cases that is very deadly. Sometimes S-shaped is there, but again, it is depending upon the situation prevailing in that area.
Okay. Microbursts are associated with single cell or with squall lines?
Usually, single cell thunderstorms, when they are very strong, they create the microburst. But from the squall line also, from the multiple cell also, the chances cannot be ruled out. It means there should be a severe thunderstorm, and from the base, when the base is coming, you know that how low the base is coming, say around only 200 meters, 300 meters. So because of the weight of the bigger drops which are coming at the lower part, the base of the cloud is coming somewhere around 300 meters, 400 meters. So in that case, the microburst, the wind is going in the downward direction. So the system should be a severe system, maybe a single cell, multiple cell are the strong.
How do ice particles and liquid droplets are distinguished to predict hailstorms?
You have seen that we put our settings that 50 dBz, and then height between 2.8 to 4 kilometers, just above the freezing level, the 2 points. Now, in the single polarization, we have to do it manually, but you will discuss about, you will see the presentations on the dual pole. In the dual pole, no setting is required, because there is a horizontal polarization and there is a vertical polarization. alternatively or simultaneously. So horizontal polarization and vertical polarization will give the clear distinction that it will be due to the water drops and it is not containing hails, or it is containing hails because the side shape will not be spherical, the shape will be slightly ovoid like this. So dual pole radar can give better information rather than a single polarization, and because of this, dual pole systems are now implemented everywhere in the world because of two reasons. Reason one, as I explained, to distinguish between the rain from the hails or from the uh, spherical water drops. And another is zeta relation is not required because it is having 4 parameters that you will see later on. On the basis of the classification of the hydrometeors is done. If these conditions are satisfied, light rain, moderate rain, heavy rain is there. So in the dual pole systems, your ZR calibration is no longer needed. But where the single polarization systems are there, ZR calibration and to know the values of A and B is required.
Next one is, what are the parameters should be analyzed for nowcasting the thunderstorm activity?
Only 4 parameters. One is VVP2. What is VP2? VPP, volume velocity processing. The vertical profile, it is available at 10 minutes interval. So what radar gives you? The radar does the volume scan of the entire system. Then from the archive data, it is analyzing 300 meters, 600 meters, 900, 1.2, 1.5, etc. What is the wind available, and it gives a vertical profile. So in this vertical profile, you can see the direction of the winds and the speed. So the product number 1 is volume velocity processing image, which gives you the time series of the velocity. You can find out whether the wind is supporting the moisture or not. If the moisture is not there, cloud will not be formed. For formation of the cloud, the temperature, that is instability, and the moisture both are required. So temperature is high, moisture is not there, no severe cloud formation, and vice versa. So in that case, if there is suppose some source of moisture is there in the southern part and the wind is blowing from the south, so VVP2 gives the idea that moisture is coming in the environment. So one is velocity volume processing, another is MAGZ, third is PPIZ, and the fourth is PPI velocity. Only 4 are required. Suppose you are not interested in the 4, only 2 are sufficient. One is VVP, where the vertical profile is there, which is very, very important. In case if I get one more lecture there just before the completion here, I'll explain only one product, volume velocity processing. There I'll show you in the sky, nothing is there, but I can say there will be a thunderstorm or there will not be a thunderstorm only on the basis of velocity volume processing here. But now, at present, you can see the MAGZ, the time sequence every 10 minutes interval, and VVP2. These 2 are enough for a forecaster to issue the warning for 3 hours. Only 2 are required.
Next one, sir. How to decide freezing level?
Freezing level depends upon the season, the place, the altitude, the latitude, and all the things are there. Radar doesn't do anything with the freezing level. Freezing level is seen from the charts, from the models, and for that test only. So next.
Is it possible to predict lightning using radar?
Yes, it's a very good question. Basically, I did not get much time. If I get 5 lectures, then I can explain you. I can detect the lightning that over this area, the lightning will strike.
I wish to see that. Yeah.
Yes. And that's why I requested that if any resource person is not available, please give me 2 hours.
Okay.
Definitely.
But still, can you give us short answer? That
Some short answers, sir.
high DBJ will.
Yes. No, I tell you one thing.
Yeah.
Lightning, there are the 2 kinds of the lightning. One is cloud to cloud. It does not harm the people, those who are on the ground. But another one which is coming from cloud to the ground here, that's very intense and very interesting to know. And it is associated with the thunderstorm. So number one, when you see in the radar that there is a very big cloud where there is a vertical extent is there, DBZ is around more than 50 DBZ, a red color is seen, and the base of the cloud is coming almost to 500 meters, then there is a chance of lightning which can fall from cloud to ground. So few things, yes, we can. So we can easily find out the location because in the map of the radar, every place is given the particular identity, some name of the station. So we can see that this area, there is a strong cloud and the base has come almost 300 to 400 meters. So there is a chance of the lightning which can fall on the earth. But remember, the lightning very rarely falls on the urban area because of the metallic structure, because of the bigger poles, because of the lightning detectors, because of the closeliness and so on. Very rarely, but mostly it is coming on the plain grounds, agriculture land, open area, and that's why unfortunately the farmers are getting killed. The people are getting. So I have given some lectures, especially on the lightning and its prevention during the rainy season or from the thunderstorm. So once again, just for a minute, that whenever there is a strong system is there, we should not venture in the open fields. No. Should not stand under the trees. No. We should not. We should be inside a pakka house, that is a fully constructed house in an urban area. We can travel in the bus. We can travel in the car, but not on the bicycle, not on the motorcycle, not with the umbrella, not with the, because the charges are accumulated on those areas. The tree leaves are bad conductor of the charges. So charges are deposited on the leaves here. And whenever the lightning is having the negative charges on the base of the cloud and the positive charges, then it falls here. So many a times, whenever there is an open field, the charges are distributed on the ground. So lightning is having its attraction towards the ground, so it falls there. So maximum casualties are there, not in the urban area, but always in the rural area, in the open grounds. So through my lecture, this can be communicated to the society that people should not venture in the open field. They should not stand under the trees, and they may travel in the cars and the bus. They are perfectly safe.
Thank you, sir. Next question. Can radar detect clear air turbulence for aviation activities?
Yes. Turbulences are associated with the severe thunderstorms. In case of, even if there is no thunderstorm, the turbulences are there. They are known as CAT, clear air turbulences. This cannot be seen by X-band, but this can be seen by S-band and C-band. So because of the turbulences, when there is a thunderstorm, on the upper part, when the strong winds are prevailing over 6 kilometers height, the radar will show you the vertical profile of the velocity through VVP2. You can see over this area, a strong system is there. So in this upper part of the thunderstorm, there will be the turbulences. And when the aircraft is going there at the height of say around 6-7 kilometers altitude here, then there will be the lot of turbulence. In the lower part, turbulences are less. The upper part, turbulences are less. But in the middle part, the turbulences are very high. So turbulences can be detected and can be predicted. But the only thing is that when the radar is there on the ground and the aircraft is flying, then if there is a communication between the pilot and the ground personnel, then it can be communicated, but sometimes it is missed.
Okay. How to calculate value of A and B of ZR relation for a newly established radar?
Okay. If it is a single polarization radar, you have to take the observations from MACZ, find the maximum reflectivity, Z in terms of the DBZ, use the relation Z and R, but the actual rainfall you have to take from the surface rain gauges. You should not take the rain gauge, which is manual, which is giving the total rainfall. You should take the self-recording rain gauge, which is giving you every 15 minutes rainfall. So every 15 minutes rainfall and Z, these two things you have to take. So two parameters A and B can be calculated statistically. And for this, my paper is there. The evaluation of the ZR constant over the Kolkata. This I have done for Kolkata. So complete methodology is given here. So you can note down the name of the paper. The evaluation of the ZR constant over Kolkata using the Doppler weather radar. So complete methodology is there. So we have to take at least 500, 600 observations, because every time when the cloud is there, may not be necessarily on the ground, there is a rain gauge. So you have to take both the readings. One is maxed in the cloud and the reading from the rain gauge on the ground, 1-to-1. If it is there, then only you can have its comparison here. So that can be done here, but it's a tedious process. It takes a few months or few years at least.
So can dysdrometer also be helpful in this case?
Yes.
Okay.
Dysdrometer is one of the very good tools which can give you drop size distribution, drop sizes, the total rainfall, the rainfall rate. Yes, I wanted to say in my this thing here, but I missed it. So thanks those who have reminded me for the dysdrometer. It is a device which is based on the ground. It is much better than a rain gauge because it gives so many things. Dysdrometer is a very good option.
Next one is there any opportunity to access radars by us so that we can get images for our research?
Yes, for India, you can write to Director General of Meteorology, IMD, New Delhi, with a request that you want to use it for the research purpose, and this is available freely online or maybe given in your pen drive, etc. But only used for the research purpose, not for the commercial basis. You can get it. And there is an archive from 2004 till date. So there is a lot of data is available. I should say not in the brilliance. I don't know what will be the limit of the data, but it is available with IMD and you can get it. You can get it.
How area could coverage by a single radar?
How much area? What is the question?
I mean, how you can cover 200 or so much kilometers of area by a single radar? That is the
single radar. It depends upon the frequencies. X band only 100 kilometers radius. That is 100 kilometer east-west, 100 kilometer north-south like this. C band 250, that is 500 kilometers along the diameter on east-west and north-south. If S band is there, the area is 400 kilometers radius. So S band, it's very costly. C band, it is in between. X band is much cheaper than S band here, but the area wise X band is only 100 kilometers, C band 250 kilometers, S band 400 kilometers. So you can see on the website of this IMD that how the distribution of the radars is there in IMD's network.
Next one, how does a concave bend of the bow echo turns into convex bend as was shown in the PPT of a squall line event?
It depends upon the synoptic situation over that area. Suppose it is coming from the northwest. It is in the form of this concave shape. But on the other side, if the things are changing rapidly, it can become straight, or sometimes it can change its shape now. Sometimes it can dissipate in between only. But whenever there is a squall line, it is a very strong system, and up to 250, 300 kilometers, it remains in the form. It might change its shape, whatever be the synoptic conditions prevailing. But it will be there for about 300 kilometers for 4 to 5 hours.
Would thunderstorms that accompany cyclones be classified in the categories you described? Also, please provide the titles of some of your research papers related to thunderstorms. Thank you.
You're talking of the tornadoes associated with thunderstorms?
I think he wants to ask the same.
Yeah.
Question.
See, not every thunderstorm generates tornado. Tornadoes are very rare in India, but at some places, whenever some supercell thunderstorm category is there, when there is a big storm, the cell is there, and it is having its, I hope you might have seen some internal structure of the supercell thunderstorm, some animal-like structure or something like that, where the core is very intense. Usually, maybe in the single cell or the multiple cell, severe thunderstorms can generate tornado from its base. It is coming as there one hole is formed at the base here, and this air is ejected very rapidly. So this hole is very small in size, maybe say 500 meters or so. So because of that, strong winds, they are coming from the downdraft inside the thunderstorm, then they're coming to the ground here. So then it is having the rotation here. So this is twisting here. So size of the tornado is very small here. And regarding my papers, I wrote one paper on this when there was a tornado in Odisha on 31st March 2009. I sent it to the international journal, but they said that since it is only a one case study here, my paper could not be published. And as I told you that in India, not so much of the tornadoes are recorded. Some information is there. And when tornado is there, may not be some Doppler radar is there. So occurrence of both the things simultaneously is slightly rare. So one of my papers is available, the case studies of the tornado over Kendrapara in Odisha, but it is there with me now with my observations. I'll see in some Indian journal if it is possible, I'll send it and I'll inform you all.
Is 50 dBz is the cutting point for extreme condition? Is
No.
there possible of extreme condition below 50 dBz?
Usually 50 dBz, below 50 dBz, we assume that it's not very severe condition. Above 50 dBz, when, but one more thing, 50 dBz and the vertical extent, these two things are there. If 50 dBz is there and the height of the thunderstorm is not, let's say 5-6 kilometers there, it may not be very severe. But bigger is the vertical extent, larger is the vertical extent, larger is the severity. So below 50 dBz, I assume that the system will not be very severe.
As radars have lesser range than satellite, do you think satellites are more suitable for forecast?
What do I think that satellite is?
More suitable for forecast.
No, any system is standalone effective. If satellite is there, you can say satellite can do everything. It's not correct because the resolution is not good. It is looking from there and observation time is again more where the radar can take one observation every 1 minute because we can have the scanning very fast and one product can be generated every 1 minute, which satellite cannot give. On the other end, radar is having the range smaller. It cannot see the larger area. So neither satellite nor radar can have the stand-alone effectiveness. We have to combine both.
Can we differentiate a multiple cell thunderstorm from a supercell in DWR?
Yes. Multiple cell thunderstorms do not move very rapidly. No. They move 45-50 kilometers, whereas that supercell thunderstorm, which is an isolated thunderstorm, which is slightly larger in the size, single cell larger in the size, which is not showing the different individual thunderstorm inside it, a single cell having a intensity of more than 55-60 dBz, and it is moving very fast. It moves very fast. And its extent is also somewhere around 12 kilometers. So multiple cells do not move with this velocity. So you can have the categorization of supercell and multiple cell.
This question I would also like to ask, sir. Even if the DBZ is showing more than 30, would it give rain if there is not sufficient CCL?
30 dBz is not a higher value because 23 dBz means it is 1 millimeter per hour. You can calculate from the formula. 23 dBz is 1 millimeter per hour. So 30 dBz somewhere around 5-6 millimeters per hour. But you require all the things. You require CCL also. You require sufficient moisture also. Favorable conditions also. So even if 30 dBz is there, sometimes this cloud does not give sufficient and might be some drizzle and goes away.
Can you explain downdraft a bit more?
Can I explain?
Downdraft.
Downdraft, it is coming from the base. See, whenever there is a growth of the cloud, updrafts are there inside it. But so when the updrafts are there, the winds, it is taking the water particles and the hails, etc. in the upward direction, then there is a growth here. Then updrafts are prominent during the time of the growth, but when there is a saturation here, then the downdrafts are taking place in and become more dominant than the updrafts here. So Then there is this thing, updrafts and downdrafts, updrafts and downdraft. This cycle goes on continuously, and because of there, sometimes there are the turbulences and few more things are there. But when the downdraft become very prominent over the updraft here, then the dissipation of the thunderstorm takes place and the rain starts. And when the downdraft become more stronger, then they originate microburst, then downburst, or sometimes a tornado. So these three things may be originated from the downdrafts. So downdrafts are much more serious than the updrafts. Updrafts for growth, downdraft for the decay and origination of the microburst.
Do a regenerating single cell thunderstorm same as multiple cell thunderstorm?
Please repeat again.
I think the question he wants to ask is a regenerating single cell thunderstorm same as multiple cell thunderstorm?
See, whenever there is a thunderstorm, there is a generation and degeneration process is there. It is not there a single cell is continuously moving. Inside this, one cell dies, another cell is generated, another cell is died, like this. But this is a continuous process, and we feel that only a single cell is moving in. The same is the process in the case of the multiple cell. The generation and degeneration goes on, but because when the sufficient energy, moisture, and stability is provided, that time it looks like a continuously multiple cell is moving like this. But process is same.
Can we estimate icing at different level from DWR?
Yes, certainly. Because you can find out during the time of winter, sometimes when you take the radar observations around freezing level, there is a white band. White band. Reflectivity above is high, below is high. But in between there is a band which is having the lower reflectivity. This is called bright band. And this bright band is basically the location of the freezing level where the ice and the super cooled water particles are available. So water particles or the ice can be seen here very well, that this is the freezing level that can be detected by the, but not always. Especially in the winter time, you can see it.
Sir, we'll take quickly two more questions from you. The first one is VVP2 range is 30 kilometer. Beyond 30 kilometer, how to use VVP2 product for nowcasting?
VVP2 gives the idea about the direction of the winds. Actually, one of my presentation I could not do where I have categorized into the thicket. The overall wind can be divided into three parts. Lower level winds from 0 to 1.5 kilometers. This is showing you that the surface wind is taking the moisture. I am calling it as the moisture supporting wind. If it is there, if it is, then 1.5 to 5 kilometer, it is a mid-level wind, which shows that the mixture in the environment here, that the mixing taking place here, say around 1.5 to 5 kilometers, and above 5 kilometers, that is known as the driving wind. So driving wind gives the direction to the thunderstorm that it should go in the direction here. So VVP2 can be this thing cut into three parts: low level winds, middle level winds, and the upper. So this is available with me, my presentation. This I will share, and that can be distributed to the participants through this mail here. But next time, if possible, then I'll show you. And some typical cases that when the wind is having this direction, yes, we are expecting a thunderstorm, even if it has not occurred. Or we are not. So a forecaster can say, today, if the supporting wind is there, yes, we are expecting some thunderstorm activity is there. But if they are not at all supporting the moisture incursion here, whatever be the temperature, 41, 42, 43 degrees Celsius, but if the moisture is not supported by the wind shown by VVP2, forecasters will say there will be a clear sky, temperature can go up to 45 degrees, but there will be no rain.
The last question. How supercell sustained over the long period in specific place, example Mumbai floods, Hyderabad floods?
Usually, the place like Mumbai, the supercells are not found because the climatology of that area, synoptically, it is not favorable for this. Supercell requires a lot of energy, and not only in that part, this energy or the instability should be available all through its way. For example, in India, from Jharkhand and Bihar, when the system is formed over that Ranchi area that is known as Chota Nagpur region. If the system is, most of the systems are formed in the northwest of the Kolkata from the Chota Nagpur. So when it is coming there from the Ranchi, then Chota Nagpur region, then Bankura, then Purulia, then Vardhaman, then Kolkata, then Bangladesh, throughout that instability is available. That is favorable for a supercell. So supercell requires throughout its supporting synoptic conditions. Otherwise, after some time, it will dissipate. So Mumbai, don't expect. Hyderabad, don't expect. Bangalore, don't expect. You can expect in the eastern and the northeastern region. In those areas, we can expect that tornadoes as well as this, what should I say, supercell thunderstorms.
Thank you, sir. So now moving on to Dr. Shrikala, please.
Thank you, sir. Now I request Dr. Paulami Chakravarti to extend vote of thanks.
Thank you, Dr. Shrikala. I'm sharing my screen if that's okay. Please let me know if it's visible to all.
Yeah, it is visible.
Thank you. Esteemed guest, distinguished speaker, and respected colleagues, as we conclude the 7th lecture of the Radar Meteorology lecture series, it is my honor to extend the vote of thanks on behalf of the South Asian Meteorological Association and the Advanced Center for Atmospheric Radar Research and the Cochin University of Science and Technology, India. Firstly, I express our gratitude to Dr. Swagata Paira, Treasurer of SAMA and Associate Professor at BIT Mesra, India, for his dynamic welcome address that set the precedent for the lecture. We also extend our heartfelt gratitude to ABM retired Professor Dr. Ajit Tyagi sir, who is also the President of SAMA, for your inspiring opening remarks and unwavering dedication to guiding the youth of our generation with your charming spirit and knowledge. Your vision and leadership continues to elevate SAMA to newer levels every day. Thank you, sir. We would also like to express our sincere commendation and thanks to Dr. Devendra Pradhan, sir, Scientist G and former ADGM Instruments at the India Meteorological Department and Chairman of the Advisory Panel for your inspiring lecture on thunderstorms and hailstorms along with the measurement techniques. Thank you so much, sir, for your informative lecture. We also deeply appreciate Dr. Rohini Bhabar, Assistant Professor from SP University, and who is also an ECT member for SAMA, for her efforts on moderating the question session and making it a lively and productive discussion. Thank you, ma'am. And a big shout out and our heartfelt gratitude to Dr. Shrikala, Assistant Professor at CUSAT, for overseeing the entire session and seamlessly orchestrating the Radar Meteorology lecture series. Thank you, ma'am. And lastly, I would like to thank all the participants for their active engagement and contributions and those lovely questions. There was a lot to learn from all of the questions when sir discussed the answers with us. And once again, thank you all present today and those working on the sidelines for making this session a success. Thank you so much.
Thanks to Dr. Paulami as well.
Thank you.
I think we can conclude the session now.
Yes, ma'am. We
Are
can
there any
conclude.
particular comments? If anybody wants, you can share.
Usually we finish with the Tyagi sir's comment. So if Tyagi sir is available, sir, we are waiting for your.
He's not available.
Thank you, Dr. Swagata, and let me again compliment all our distinguished speaker, Dr. Pradhan, then the organizing committee members, Shrikala, of course, the Rohini and Paulami for organizing and conducting this session very, very effectively. We are missing many of our colleagues who are today used to be there, Dr. Someshwar Das, Abhilash, Lakshmi. They are probably busy in preparing to visit to Japan for DVEX conference. So wish them all the best. And lecture by Dr. Pradhan as always has been insightful, informative. It's replied to all those questions asked in question answer session very, very effectively, and I'm sure all participants have benefited. And this is an important part of the radar observations, the thunderstorm, severe thunderstorm, squall line, hailstorm, their detection and the forecasting. Thank you, Dr. Pradhan.
Thank you, sir.
For delivering today's lecture
Thank you,
and
sir.
supporting this series of lectures also. Thank you.
My
Just
sincere thanks to all, President Sama, Dr. Ajit Tyagi sir, Dr. Swagata, Dr. Paluma Chakrabarti ji, and everyone who has conducted very nicely. I am grateful to everyone. Thank you, sir.
Just for a note, today you have answered more than 25 questions, which is not very usual in our lecture series.
True.
That's
Dr.
good.
Swagata, similarly, he answered, I think last time also, maybe around 25 to 30 questions.
Uh,
It's
and
very nice to hear him.
yeah, and Dr. Mohan gave a message that he is in transit at Bangkok.
Really happy to see you, everyone. I missed the program today.
No, never mind. All the best. Enjoy your trip. And I understand you are going to hold a summer side meeting also there. So that will be great.
Thank you, sir. Thank you very much. Thank you, Pradhan sir, for your excellent talk.
Okay,
Thank you, Dr. Das. Thank you.
So now we can close it.
Thank you, sir.
Okay,
Thanks, everyone.
Thank you, sir.
Bye.
Maybe you can end the meeting.
The speaker is ready. And why does the speaker ask the ball to read? See, the speaker क्या टेम्परेचर क्या हो रहा है?